All right, folks, today we're going to talk about representing motion notes, motion graphs, and a little bit of equations based on velocity and displacement. So I'll kind of get going. If you guys take a look, you guys can fill these in. You can use these notes for when you go to take the quiz or the test or any of your practice problems. So this will not be submitted, but this is definitely something that you should complete and keep for yourself. So you could either do it digitally, or if you want to print it and handwrite it, you can certainly feel free to do that. All right. So here we go. Oftentimes people think, motion obviously is something that's moving, but something that's important about identifying a reference point is, we can say that an automobile is moving 70 miles per hour on the freeway, and we just assume automatically that the reference point obviously is the road. But in the world of physics, when you get a little bit more technical about certain things, there's a lot of different realms of what's distance measured by, or what's displacement measured by, like where do we start, where's zero, where's the end, and so forth. So I could propose the question and say there's people sitting in the classroom, or right now you're sitting at your desk or your table, and I could ask you what is your velocity, and the common question would be or common answer would be to say that I'm not moving at all because I'm just sitting in my seat. Well, it would be correct that you're not moving maybe relative to the floor or relative to your room or whatever it is, but if we changed the reference point all of a sudden and said, are you moving relative to your position from the sun? Well, then now all of a sudden you would have to say, well, of course I'm moving. I'm orbiting around the sun, and we're rotating on our axis, so you're actually kind of, spiraling like a corkscrew almost going around the sun if that was your reference point. So just taking an analogy like that, all of a sudden you can kind of see how the reference point becomes quite important. So as you go on and you label diagrams and pictures and so forth, you need to kind of determine what is the reference point when you're determining, say, distance or velocities and accelerations and forces and so on. So there's various types of motion: circles and waves. Waves also cover oscillations. Waves can be not just mechanical waves such as sound waves or surface waves or seismic waves, but we'll also talk about electromagnetic waves, light, electricity, all of that. A motion diagram can simply be a picture of a person or an object, and normally the frames or snidbits that you see in the diagram are taken at an equal interval of time, or taken at an equal distance or some sort of measurement, so that you can see where and when the event is happening. So in this picture here, there's no times or distances, but we could very easily say, add it to the diagram. You don't have to draw a detailed picture of the item or the person, whatever. Sometimes it could be something as simple as just dots on a line. But a motion diagram is generally going to show a reference point, an object, distance, and or time. Something that has a magnitude and a direction, and it can represent any vector quantity. Force and velocity are both the most common vectors we'll talk about here in the future. Momentum is in there also, but as we go, we'll kind of apply them more specifically. But simply put, a vector can be broke up into two components. So if this is vector A, you can always break it down into the horizontal and vertical components, which you would call A of X and A of Y. And you can do the same thing for vector B. Even though it's pointed in this direction, we can break it up into the X and the Y component. So this is B of X and B of Y. The reason it's important for us to break these into horizontal and vertical components is if we want to actually add these vectors together and not use like law of sines and cosines, if you want to keep it a little bit more simple and just stick with your basic trig functions for right triangle, sine, cosine, and tangent, you need to summarize the X and the Y components individually before you can add them together. Because vectors can only be added together if they are collinear, which means they're pointed in the same direction. For example, vector A and B from the start are not pointed in the same direction, so they can't just be added numerically. We can't just add, if this was 7 and this was 4, we can't add 7 and 4 because they're not in the same direction. However, if we break these up and figure out the A of X here to be equal to 3 and the a of y here to be equal to 2 and this b of x here equal to 1 and this b of y here equal to 4, then when we go to plug them all together from here to here, I know that the a of x plus b of x in the horizontal direction is just equal to 4, and my a of y plus b of y in the vertical direction is just equal to 6. And you could draw the right triangle and summarize the resultant vector. And delta means change. It's the same thing as change. I'm sure you've seen it potentially in chemistry. There's other classes that would use it also, but when you see that, it means it's a rate of change. We'll have changes in velocity, changes in acceleration, changes in distance and displacement. It's just a common symbol that's used. So the example problem that's given, if you're going to list all of the variables and you want to find change of time, you're going to list time final, time initial. Time final is 7.47 seconds. Time initial is 5.46 seconds. You get 2.01 seconds as your change of time. Pretty straightforward. Basically put, distance is the length of the path traveled and displacement is the straight line distance between the two. If our start point is position A and our finish point is position B, if I walked all the way down this path, not taking a straight path from A to B, maybe this is a distance of 8 meters, but from start to finish, from what we're considering start to finish, if the distance as the crow flies, or straight line distance between the two, is only 6 meters, this is known as the displacement and this is known as the distance. Example problem number 1, Jimmy ran in a perfectly straight line, traveling 50 meters from his starting position. What is his distance? What is his displacement? Well, if we start here at 0 meters and he walks in a perfectly straight line 50 meters from wherever he started, if that's his situation, his distance is equal to 50, his displacement is equal to 50, because he did not take a curved path. Now we can do the complete opposite. Sally ran in a perfect circle around the field on a path of 200 meters, starting and stopping in the same place. What was her distance and what was her displacement? Well, if you start here and she runs in a complete circle, the distance that she traveled is still equal to 200 meters. She had to run that distance or walk and go all the way around. However, if her starting position and her ending position were in the exact same place, her displacement would actually be equal to 0 meters. Because from what we're calling start to finish was the same position, then she didn't go anywhere. So this is similar, related to the frame of references. What are we considering the frame or reference or position? The start point is the finish line, and reference being the field or track that you ran around. Notice that in your y position, or sorry, the y-axis here is position or distance, and the horizontal axis is time. So this is where we start, and the first segment that they have us look at is the first 10 seconds. So from here to here, we can see that the line has a positive slope, the distance becomes more, and the time has elapsed. So I know that from the 0 to 1 seconds that this person moved forward, the actual velocity here, or the rate of change, I would know it's equal to 6 meters per second. Here. So there was basically no motion. 0 meters over 5 seconds is still equal to 0 meters per second. And then if we look at the difference between 15 seconds and 40 seconds, they went all the way from 60 down to negative 40. What's happening here is the person's moving backwards. Now this doesn't mean they're slowing down, they're just moving in a negative direction. So the slope of this line, the steepness of it tells the magnitude, but the fact that it's negative is just saying that they're moving backwards. So they traveled a total distance of 100 meters, because they went from 60 to negative 40. So they went a total of 100 meters in 25 seconds. It would be negative 4 meters per second. I guess I can put that there if you want. And then the very last one's the 40 to 50 second mark. And I believe this ends up being 2 2/3 meters per second. Something like that. Okay? Velocity, the equation for, is distance over time. This can be rearranged 3 different ways if there's 3 variables. Quick example. Car was driving down the road. They travel a distance equal to 10 meters. So you're literally going to punch that in. 10 meters in 5 seconds gives me 2 meters per second. Just like I showed prior, this d of I is initial distance, or distance initial. So you can think of this as a start point. Thinking again of frames of reference, if we're considering a person or an object. So the first example says how far will an object travel from a starting point if its initial position is the distance from the origin. Well, we know that distance is velocity multiplied by time plus the initial distance. So if we want to figure out the total distance traveled, we'll take the velocity, 5 meters per second, we'll multiply it by the time, 10 seconds, and we'll add the initial velocity, or initial distance, which is 0 meters. So 5 times 10 gives me 50 meters west of wherever our start point was. Or will an object be from its original position? If it starts 5 meters, I was going to draw an item for this, or assuming that they are traveling north the whole time. It started 5 meters from what we're considering the origin to be, and then they're going to go 50 meters per second for a total of 20 seconds and continue to go north. So we want to figure out what that total distance is. So you're going to have velocity multiplied by time plus the original distance. Velocity 50 meters per second, time 20 seconds. Starting position was equal to 5 meters, so that's already done. So we multiply the 50 by the 20, 1005 meters. So that means the additional distance from here to here is a total of 1,000 meters, and our finish point would be 1,005 meters. So there's that. In the example that's given, this is showing distance versus time, or position versus time. If there's ever lines with a positive slope or they're going up, it represents that the object is moving forward. If you see straight lines on a graph, so hence this and this, it means the object's traveling at a constant speed. The slope never changes. So from here to here versus here to here, the green line is steeper, which means it's going faster, and the red line for this first portion means that it's moving a little bit slower, but they're both moving at a constant speed. If you look at the red line here where it flattens out, the distance doesn't change, your y variable doesn't change, and the time does. So that means the object came to a stop, and then you'll see this negative slope for the object going down, meaning that it's traveling backwards. So it doesn't mean it's slowing down, it means it's stopped and now it's moving in reverse at a constant speed. Curved lines, on the other hand, if you see a curved line like the blue one, a curved line represents acceleration. So if something's accelerating up or has a positive acceleration, it means the change in slope is positive. So starting here, if you think of a line that's tangent to the curve, something that looks similar to this, it starts out with a low slope. As it gets a little further, the line gets a little steeper, and you get a little bit further, and the line gets even steeper yet. So the slope is increasing, which means it's getting faster and faster and faster. Now, if you wanted to see what a graph looked like for an object that was slowing down, if it's a deceleration, it's also going to be a curved line, but it's just going to be curving the other way. So I'll pick the green line here, for example. This object travels at a constant speed, and let's just assume that it slows down and comes to a stop. The green object is representing a fast and constant speed, but let's assume that this object slowed down and, say, came to a stop. So we know stationary is horizontal, no change in distance, no slope. So if we were traveling at a constant speed and all of a sudden started to hit the brakes and slow down, the line would curve, and then if we came to a stop, the line would flatten out. So the curve, this area right here, is what's showing the deceleration or the slowing down of the object. These two graphs are showing the same item. So remember, we start out with a slope that's quite vertical. So this object right here, when it starts out, is going fast. A little bit further on, it's going slower, and then it gets to a point where the position time graph goes flat, which means the velocity goes to 0. If you look at the velocity graph, it starts out fast and goes slower and slower and slower and gets to 0. I could conclude, wherever this point is, where the line gets flat, let's just say, for example, that's 5 seconds. I know that the deceleration lasted 5 seconds because as soon as velocity goes to 0, they're gonna match up. So again, these are the same item, different graph. This is distance or velocity versus time. This is velocity versus time. Now for the next one, we got a position time graph. This is an object that starts out at a positive distance. It's moving in reverse, moving backwards, so it has a negative velocity all the way up to this point, and then it starts to decelerate and come to a stop. So there's kind of 3 parts to this one. So let's just say, for example, this was 5 seconds, and let's say that this was 10 seconds. So the first 5 seconds, it's got a constant negative velocity, which is represented here. Negative position, negative velocity, there's your first 5 seconds. And then over the next 5 seconds, this is producing a curved line, which is showing a change in velocity, which is represented here by the changing velocity, so it shows the slope. There's your 10-second mark. And then the long flat line here is just showing no velocity, and if you look in the velocity graph, that actually goes to 0 also. So here's an example of distance, velocity, and acceleration time graph all plotted out for this. Again, these are all the same item now. This is basically, I don't know what would be a good example. This might be someone tossing an object into the air, letting it float up into the air, come to a stop, and then kind of fall back down. So again, a distance time graph, they break it up. Here's the first segment that they give you is from here to here. Curved line on the distance time graph, curving up, means a positive velocity, an increase in velocity. And on an acceleration time graph, it shows the acceleration is positive. Now all of a sudden you have a break in the graph. On the distance time graph, you get a straight line now without any curvature all the way up to this point right here. It's a straight line. It's going up, but it's straight. It's not curved. Constant velocity. So on the velocity graph, you have a flat line because it's